Okay, welcome back to Chapter 7 in our Zane State Physics class, where we are talking about momentum. And we're going to continue our discussion of momentum by talking about impulses. So we had stated earlier that force, or the sum of forces, is equal to the change in momentum in a certain period of time. So change in momentum over change in time. And so if we solve that formula for this term here, we see we would just multiply both sides by delta t, and we get this. Force times delta t equals delta p. And what this delta p, this change in momentum, has a name. It's called an impulse. So an impulse is F delta t. It's force times the time. And usually this change in time is a very small period. It doesn't necessarily have to be, but it usually is. So like in the example here of a tennis racket hitting a tennis ball, that force is delivered to the tennis ball over a short period of time. And when you take that force multiplied by that short period of time, what you get is an impulse. Now, if we look at it technically, the force that's imparted from one object to the other, it starts out at 0, but it kind of takes a little while to ramp up. So imagine this part of the curve is where the tennis racket is hitting the ball, and they're compressing, and then the netting of the racket is bending back, and then it reaches its maximum point here, and then the ball starts to leave the net and the racket, and the strings bounce back until the two are no longer in contact with each other. So you get this curve with a peak in it. You've got this maximum force spread out like a bell curve over time. So in order to simplify our calculations, what we do is we take the average force over this time period. So what we end up with is this shaded region here. If we were to compare areas, we end up with a nice, neat rectangle, which is much easier to calculate that area. So when we take average force times delta t, it gives us this shaded region, which is the impulse, which is approximately equal to the area under this curve, which would be much more difficult to accurately calculate. So when we're talking about the force times delta t in an impulse, we're actually using the average force, not the maximum force. And so there are some benefits to spreading out delta t in an impulse. So in terms of safety, the shorter this time period is, so if we're going to keep an impulse constant, okay, if the delta t goes down, then the force has to go up in order to keep that impulse value the same. So conversely, the longer you can make delta t, the longer you can stretch it out, the less the force is. And so that's the reason behind things like airbags. When a car crash occurs, the person if there was no airbag, would fly into the dashboard or windshield, and that sudden impact is obviously very dangerous to the well-being of the driver. If you can slow down that impact by increasing the amount of time it takes between the person and their surroundings, then you are lessening the force. So the textbook also gives the example here of Bending your knees when you land decreases the amount of force or the impact or impulse on the body because you're stretching out that time a little bit more. Or why airbags or landing on a pillow hurts less than landing on concrete. So we are stretching out that delta T to be longer in order to decrease force. So I may have mentioned earlier that momentum, yeah, I believe I did when we looked at the train cars colliding with each other. Momentum, like energy, is conserved. So we can look at a situation usually involving a collision, is what we're investigating, and the total amount of momentum before the collision will be equal to the amount of momentum after the collision. It's just that that momentum may get transferred from one object to the other. And directions may change. After the collision here, object A traveling to the right has bounced back to the left. And they don't always have to bounce off of each other and go in different directions. The two objects may end up going in the same direction. But yeah, so momentum is conserved in collisions, but we have to remember that it is momentum in a line. So momentum is a vector, just like velocity. So the momentum along this line is conserved. We'll talk a little bit about 2 or 3-dimensional collisions in a little bit. We can further describe collisions as elastic or inelastic. So in an elastic, easy for me to say, collision, all of the kinetic energy is conserved. So billiard balls are a pretty good approximation of this. When one billiard ball strikes another, they don't deform very much. They keep their shape, and that kinetic energy is transferred from one to the other, and very little of it is lost. In a purely elastic collision, none of it would be lost. Versus, and if you go through my PowerPoint, I've got posted on Blackboard. I actually have a video here from the slow-mo guys where they film this in slow motion. The soccer ball, which is actually in the video filled with water to give it more mass or more momentum, hits the guy in the face, and you can see the shape of the ball itself. It gets compressed. The guy's face goes through all sorts of weird contortions. And so this would be an example of an inelastic collision, where a lot of this kinetic energy, instead of being transferred in a straight line from one object to another, actually gets transformed into thermal energy, sound energy, lots of deformations occur. It kind of spreads out in different directions. So it gives a little bit of an appearance that the momentum is escaping the system or just going away. It's not really. It is still conserved. Momentum is conserved. It's just that it is being transformed into other forms of energy. So it doesn't entirely remain kinetic. So again, this slide is essentially illustrating what we've been talking about, whether we're talking about billiard balls hitting each other or train cars. We have two objects in a straight line with each other that have an initial momentum and velocity, momentum and velocity. In this example here, object A has a larger velocity, and it's going to overtake this one. They're going to collide, and some of that momentum is going to be transferred onto object B. So again, we could maybe picture billiard balls, one that is rolling slowly, one that's rolling more quickly. The faster one overtakes it and actually rear ends it, collides with it from behind, and then transfers that momentum to the other object, and now it's going to move faster, and the first one is moving slower. But the sum of m times v, the momentum of the two objects, if we sum momentum of object A, plus the momentum of object B, after the collision, it's going to still equal momentum A plus momentum B prior to the collision. So, and again, this is in one dimension, just in a straight line. And I keep mentioning that because if we contrast that with a two-dimensional collision, it definitely gets more complicated. The math does. Let's look here at an example problem. Hopefully I can get this done before my 15 minutes are up, where we have a billiard ball A with velocity A is going to collide head-on with a ball B of equal mass. What are the speeds of the two balls after the collision, assuming that it is elastic? So this first line here is basically stating the conservation of momentum for a head-on collision. We're going to assume that we have two billiard balls that are going to hit each other head-on, and like the other examples we've looked at, we know that the after the collision, the momentum is going to be the same before the collision. So we have whatever, and also mass has been taken out of this equation because we are assuming equal masses. So initially this would have been mva plus mvb, but since the mv prime a plus mv prime b, since both of these objects have the same mass, we can just divide that out of the equation, so all the masses go away. So the sum of the velocities of these two objects before their collision is equal to the sum of the two velocities after the equation, or after the collision. Okay, but this essentially yields us an equation here with too many unknowns. We can't really definitively solve anything with this equation alone. So we have to then also look at this conservation of kinetic energy. So this is equation 7.7 in the textbook. You can look in the book to see how it is derived, but it basically comes from the conservation of kinetic energy. So 1/2 mv squared for object A plus 1/2 mv squared for object B before the collision is equal to the sum of their kinetic energies after the equation. And so again, with the masses being equal, they cancel out, and the equation gets simplified, and we end up with this. So this is an important equation to note. I believe you will need this for at least one of your homework problems. Comes from the conservation of kinetic energy. And we have velocity A, velocity B prime, and velocity A prime. The same variables that we have up here. So we have two different relationships for these variables. And so we could substitute, method of substitution, solve these two equations simultaneously. But this is a situation where adding the two equations together is going to be a simpler method. So if we add velocity A and velocity A, we get velocity A. The velocity B and negative velocity B will cancel each other out. These terms will cancel each other out. We'll end up with 2 velocity prime B. We divide both sides by 2 and basically end up with this equation. And if we subtract these two equations from each other, we end up with this. So basically, the conclusion we're drawing here is that the final velocity of object B is going to be equal to the initial velocity of object A. and the final velocity of A will equal the initial velocity B.